Hi again. This is the fourth module. Recall that in module number 3, we started talking about a probability review. We defined omega F and P, the outcome space, the event space, which is a field, and the probability function. We then talked about joint probabilities, conditional probabilities, independence, and also Bayes rule. And now we're going to move to random variable. So a random variable denoted by RV is a function of an outcome of the random experiment. So earlier we said that we had omega, and we had two different outcomes in our earlier example, heads and tails, H and T. And now we're mapping them to a real valued number. Head will be mapped to 1, tails will be mapped to -1. And now these could be different numbers. Heads could be mapped to 12 and tail to -7. It doesn't matter. Now, that example is looking at two outcomes, and the example that you worked out with tossing a die has 6 different outcomes, but probability spaces often have lots of outcomes, even uncountably many outcomes. So we'll gradually work ourselves through more interesting examples. So here's an example of a random variable. We'll spin a wheel and we'll observe an angle theta that's between 0 and 2 pi. And we want to see where it lands. So the sample space, omega, is going to be all the angles theta between 0 and 2 pi. So we have uncountably many possible outcomes. And the event space will be the some set of subsets over omega. What is a reasonable set of subsets over omega? There are problems when we're dealing with uncountably many types of cardinalities of sets. So what we're going to do to overcome that problem, we're going to take countable unions of intervals within omega. An interval meaning from A to B. And it could be close to A to B, open from A to B, etc. All these things, because we have closure to complement, closure to intersection, closure to union, all these things can be supported. They're all analogous, okay? So we're just gonna have a countable union of intervals. Now the probability space is going to be the sum of the lengths of the disjoint intervals divided by 2 pi. Now recall, we have a countable union of intervals. Because of that, when we're looking at disjoint intervals, we're going to have a countable number of disjoint intervals. And when we take the sums of their lengths, the sums of lengths of a countable number of disjoint intervals should be well defined. In contrast, this type of problem could be very complicated if you didn't enforce the countable type of aspect, okay? So here's a possible random variable x. X is going to be an outcome, a function of the outcome. The outcome, lowercase omega, is an element of the outcome space, capital Omega. And x is going to be 1 if the angle is greater than pi. The rest of the time, x is going to be 0. So we're going to have a 1 only if the angle is between pi and 2 pi. The next definition is a cumulative distribution function, which is often abbreviated as CDF. It maps a random variable, or RV, to a probability space. The CDF is a function over real numbers, and it's the probability that the random variable is less than or equal to a number. Okay, so again, it's a function, and the input of that function is a number, which in this case is the number C, a real value number. And the output of the function is the probability of all the outcomes such that the random variable, which again is a function of the specific outcome, lowercase omega, is less than or equal to C. For different C's, we're likely to have different probabilities, different CDFs. Now, this function is well defined for both discrete or continuous valued random variables. And let's look at an example. Recall our coin flipping experiment. We had heads or tails, H or T. let's map h to 1, t to -1. I said that, well, earlier I had an example where each of them were probability 0.5. I modified them. One was 0.6, another was 0.4, but forget about that. Let's look at the simple case where each has probability 0.5. And let's calculate the probability, or rather the function fx of c. So fx of c is the probability of the set of omegas, so the set of lowercase omega, which I'll denote by w, is an element of the set of outcomes omega, so w is an outcome, such that the random variable x as a function of the outcome is less than or equal to c. All right, so now first we're going to take c equals 0. Or rather, no, we're told in the last line of the slide, we're told that we're going to look at c less than -1, and then we're going to look at c greater than or equal to 1. So let's begin with c less than -1. So we're looking for the probability of the lowercase omegas such that x of omega is less than or equal to c, which is less than -1, meaning that x of omega is strictly less than -1. But if we're looking at the definition of our random variable, it's either it's mapped to +1 when we have a head, -1 when we have a tail. It's never mapped to anything less than -1, and therefore x of omega is never less than -1, hence the probability is 0. And because of that, fx of c less than -1 is equal to 0. The next case is c greater than or equal to 1. So we have the probability of all the outcomes lowercase omega such that x of lowercase omega is less than or equal to c, and c is greater than or equal to 1, so let's just write that it's less than or equal to 1. Now, this is the probability of, let's think of what omegas satisfy this. Omega can be h or t. If omega is h, we have a 1. And indeed, x of omega, which is 1, is less than or equal to 1. That's fine. And if omega is t, the random variable is -1. -1 is definitely less than 1. So therefore, this is the probability of omega being t or h. Omega is always t or h. That happens with probability 1. And therefore, fx of c in this case, which is greater than or equal to 1, is equal to 1. What happens in the middle? C is in the range, in the interval, which strictly includes -1, up to the number +1, not including the +1. In this case, the probability of omega, such that x of omega is less than or equal to c. Now recall, c is greater than or equal to -1. So if omega is equal to t, then x, when we have tails, is -1. And when we have, in that case, -1, then -1 is less than or equal to c. That's correct. And on the other hand, when we have heads, we have +1, and +1 is strictly greater than c, because recall, c is in that interval which does not include the number +1. So here we have the probability of w being only equal to t, and that happens with probability half. So fx of c, in this case, is 0.5. Now, if we plot this, the horizontal axis will be c, the vertical axis will be fx of c. I'd like to request that when you're solving through a homework or a project or a test, please label your axes and also show the scale, because without that information, it's very difficult to understand what's going on. And here we saw that the interesting values of c occur at -1 and at +1. And let me just switch color so it'll be easier. Below -1, fx of c was 0. At -1, it jumps to half. And when c is equal to 1, we jump to fx of c is equal to 1. All right, so that's this example, and whether the discontinuity is right before the -1, right after the -1, at the -1, these details you can think about later. All right. The next topic is the probability density function. We talked about the probability, the cumulative distribution function, or CDF, and now we're taking its derivative. Lowercase fx of c is the probability density function denoted by, or abbreviated by, PDF, and lowercase fx of c is the derivative of capital fx of c. And formally, we're looking at f sub capital X for the random variable. Lowercase x is the value that we're looking at, and we're evaluating the derivative at x being equal to c. This is well defined only for continuous valued random variables. For example, on the previous slide, we had this discrete valued random variable, and the CDF had these two discontinuities at -1 and +1, and the discontinuity in the CDF would mean, well, one way to think about it is that the derivative is a delta function, but that might be complicated. Instead, we're just going to assume that if we have a continuous valued random variable, we don't have discontinuities in this CDF. So what's the meaning of the PDF? The interpretation is that where the PDF is smooth, let's look at the probability of the random variable, capital X, its value being between lowercase x and lowercase x plus delta. So that's the CDF of x plus delta minus the CDF of x. And again, we're assuming that the PDF, the derivative, is smooth. So in that case, between x and x plus delta, the derivative is approximately fx of x. Lowercase fx of x is the PDF. Recall that the capital F is the CDF. And we're multiplying the derivative, lowercase fx of x, by delta, the duration, the width of this interval. For example, here we have an illustration of a Gaussian random variable. We'll be talking about that distribution in a moment. It's a bell curve, and we have 2 points on the horizontal axis, A and B. And the probability of being in this shaded area between A and B is an integral from A to B over the density function times dx. In this case, they called it P of x. I call it F of x. It's just a matter of notation in this plot that I copied from somewhere. All right, so taking the limit, the probability that x is between A and B is, once again, an integral from A to B of the PDF multiplied by dx. So here are two common random variables, and as I said, we are somewhat more interested in continuous valued random variables where the PDF has this nice smooth form. One of them is a uniformly distributed random variable, and x will be denoted as UAB, meaning that it's uniformly distributed over the interval from A to B, and this is a closed interval. it's closed because of these square brackets. And we could have had an open interval or a semi-open, semi-closed interval. We could have had different things, okay? But just to keep it simple, here we have a closed interval. And now let's take four numbers A, C, D, and B. So this is going to be the real line. And A is smallest. Then we have C. Then we have D. And then we have B. And we're saying that we're uniform between A and B. And we're asking what's the probability of being between C and D? So the probability of being between C and D is the length of the segment from C to D, namely the segment from C to D is D minus C, divided by, in this shaded blue, I'm dividing by the length of the larger segment. And the length of the larger segment, it goes from A to B, so its length is B minus A. On the other hand, imagine that you don't have this interior segment from C to D. We only have one number, C, which is between A and B. And the probability of being less than or equal to C, that's the cumulative distribution function for fx of C. So that's the probability that x, the random variable, capital X, is less than or equal to the value C. That's the length of this segment, C minus A, divided by the shaded B minus A from before. Now, recall that the PDF is the derivative d to dx of the CDF, and taking the derivative gives us the PDF, the probability density function. Fx of C is, well, the derivative of C minus A divided by B minus A. So C is really a variable. So we're taking a derivative with respect to D, with respect to C, assuming that it's in that interval. The derivative of the numerator, C minus A, is just 1 because we're taking a derivative with respect to C. And we're dividing by a constant, B minus A, and therefore the derivative is 1 divided by B minus A. So that's a uniform random variable. The next example is a Gaussian random variable, the bell curve that we saw earlier. We denote X as obeying a normal distribution, N for normal. It's called Gaussian, it's called normal. There are different names for it. And it has parameters mu and sigma square. Mu is the expectation or average, and sigma square is the variance, which is the mean squared error around the expectation. The PDF, fx of x, for this Gaussian, this parametric Gaussian distribution, will be 1 divided by square root of 2 pi sigma square, again, sigma square is the variance, multiplied by e to the negative. In the numerator, we have x minus mu square. Again, mu is the average, the central value. So this would be x, this would be f capital X of x, and this bell curve would be centered around mu. And e to the negative x minus mu squared, so how far we are, the square distance from mu, divided by 2 times the variance sigma square. So 2 different commonly used random variables, uniform and Gaussian. What about a conditional probability? We talked about conditional probabilities, we talked about joint probabilities. We also have these concepts in the CDF and PDF worlds. The motivation is that we want to characterize a random variable conditioned on another event or another random variable. And conditional distributions involve the part of the probability space which is being conditioned on some event. So conditional CDF fx of a value x conditioned on an event A is the probability that the random variable denoted capital X is less than or equal to the value denoted by the lowercase x conditioned on the event A. So that's a conditional CDF, and the conditional PDF, similar to before, is the derivative of the conditional CDF with respect to the value lowercase x. So that's a conditional CDF and conditional PDF, and we also have joint. The joint cumulative distribution function, or joint CDF, is a function of both x1 and x2. Lowercase x1 and lowercase x2 are individual values for the two random variables, capital X1 and capital X2. And it's defined as the probability that the first random variable, capital X1, its value is less than or equal to x1, lowercase x1. And the second random variable, capital X2, its value is less than or equal to lowercase x2. So you may want to think about this as a two-dimensional world. We'll have one axis, the horizontal axis will be for the random variable x1, and the second axis, the vertical axis, will be for the variable x2. And imagine that lowercase x1 is some value, and lowercase x2 is another value. And this point that represents the two of them, the joint CDF is the probability of all the points in 2D, all the values for the two random variables, capital X1 and capital X2, that are both less than or equal to x1 along the first dimension, the horizontal dimension, and less than or equal to x2 along the vertical dimension, or this shaded area. The joint PDF is a two-dimensional derivative of the joint CDF, and it's possible to give a graphical interpretation of this area where the width along the horizontal axis would be dx1, some infinitesimally small width, and the vertical width would be dx2. And when we're taking the probability of this small rectangle and both of its sides, the limit goes to 0, the ratio between the probability and the area, that's the joint PDF. Okay, so that's a possible graphical interpretation. Expectation, so we're getting close. We'll have variance too. Expectation is an average. For discrete random variable, the expectation of x, which is denoted by E of x, the x is going to be in square brackets. It's a summation over the possible outcomes, where because it's discrete valued, we index them by I. And we, inside the summation, we're summing over xi, the value of outcome number I, multiplied by the probability that the random variable equals xi. So it's a weighted average where we weight over the probabilities. If you have a fair coin toss, 50-50, you'll have 50% times the first value, which earlier was +1, and 0.5 times the second value, which earlier was -1. But these could be different probabilities. It could be that one of them has 0.6 and the other has 0.4. So it could be a weighted average. For example, if we're tossing a fair die and it has 6 sides with values 1 through 6, each side has probability 1/6, and the expectation of this random variable is the summation over the values multiplied by the probabilities. The probabilities are always 1/6. The values are 1 through 6. So we're taking a summation over 1 + 2 + 3 up to 6. And we're multiplying all of these by 6, which means that we're dividing by 6. And 1 + 2 + 3 up to 6 can be shown to be equal to 21. And 21 divided by 6 can be shown to be 3.5. Now, there's a trick. The trick is that the 1 and the 6 are symmetric. The 2 and the 5 are symmetric. The 3 and the 4 are symmetric. The 1 and 6, they sum to 7. The 2 and 5 sum to 7. The 3 and 4 sum to 7. And each of these 7s, half the time it's a lower value, half the time it's a higher value, but on average, half of 7 is 3.5. For a continuous random variable, the expected value of x is an integral over the value x multiplied by the PDF fx of x dx. For example, if we have a uniform random variable between 0 and 1, the expected value of x is an integral over x fx of x dx. We're integrating from 0 to 1. Those are the ranges of this interval. We're integrating over x dx times the probability density function. The probability density function is equal to 1 because recall that fx of x was 1 divided by b minus a in our example from 2-3 slides ago. B is equal to 1 here, a is equal to 0, so the probability density function in our example is 1. So we're integrating over x dx from 0 to 1, and the integral of x dx is x squared divided by 2. Evaluating that at 1, x squared divided by 2 is half. Evaluating that at 0, x squared divided by 2 is 0. Half minus 0 is equal to half. This confirms our intuition that we're uniform between 0 and 1, and the midpoint is at half. All right, next slide, and I somehow forgot to clear the drawings. Variance and standard deviation. So the variance is the mean squared error around the expectation. So it's defined as the expected value of, we take x, we subtract off the expectation, and the squared error is the square of x minus e of x. So this is the error. And squaring it gives us the squared error. And we're taking the mean, which is the expected squared error. So that's the variance. And the standard deviation is the square root of the variance. So the variance has units of squares of numbers, and the standard deviation has units of numbers. So for example, earlier, when I sketched a Gaussian distribution, and this was mu, the average, then the width of the lobe is proportional to sigma, not sigma square, but sigma. And again, this symbol means proportional to. Prop 2. Now it could be 3 sigma, could be 1.5 sigma, depends on how you define it, but it's proportional to the standard deviation. So let's calculate the variance for this uniform distribution that we saw on the previous page. It's uniform from 0 to 1. We saw that the expected value was half, and let's calculate the variance. The variance is defined as the expected value of x minus its expected squared. The expected is half. Therefore, we're substituting for e of x, we're substituting half, and we're taking the expected value of the square of x minus half. So what is x minus half squared? It's x squared minus x plus a quarter. And it so happens that expectation is a linear operator. Because of that, expectation of sum of terms is equal to sum of expectation of each of the individual terms. Okay, so we have the expected value of x squared minus the expected value of x plus the expected value of a quarter. Well, a quarter is a constant. It's always a quarter, and therefore the average, the expected of a quarter is a quarter. We know that the expected value of x is half. We saw that on the previous slide. And what about the expected value of x squared? So the expected value of x squared is an integral over x squared f of x dx. fx of x is the PDF. And the integral over x squared, recall that the PDF is 1. So we have an integral over x squared dx, which is, we're evaluating x cubed divided by 3 at values 1 and 0. At 0, it's 0. That's simple. At x equals 1, x cubed divided by 3 is a third. So the expected value of x squared is a third. Now we have that the variance is the expected value of x squared, which is a third, minus, with this underline tilde sort of thing, the expected value of x, we're subtracting half. And then the expected value of a quarter is a quarter. All of these terms, they have a common denominator. They can be expressed as different integers divided by 12. A third is 4 divided by 12. Subtracting half, we're subtracting 6 divided by 12. And adding a quarter is adding 3 divided by 12. 4 minus 6 plus 3 is 1 divided by 12. That's the variance. And the standard deviation is the square root of the variance. So that's it, and we'll continue next time.